situation where it can be determined. In fact, a lot of cases, the answer that was given during which minute were the most people in the store was the minute in which the most people were entering the store. This minute here. Minute where fewest people were in the store, the minute where fewest people were entering the store, and most people leaving the store. The statistics are a little bit sobering there. They were given plenty of time. And this is not a one-off experiment. This experiment has been replicated in school after school after school. By the way, I'm not turning this into an experiment. I'm in no way planning to report the results of this. It will stay within us as a class. However, this experiment has been replicated worldwide. And what it shows is that people are surprisingly limited in terms of their ability to eyeball a situation and muse about it and render answers which are accurate. So let's go over these things. Yes?
Are these numbers consistent across the graphics? Because this is one particular thing. Most people
right.
from MIT are pretty smart.
That's right. For STEM individuals, I believe these are similar across different schools. But, in other words, science, technology, engineering, math. But for other demographics, I think they vary. There's actually a substantial literature that's been developed on this where people have reported results, and I do believe there's some variation. The implications of this may seem very mild for something like this. After all, your life doesn't hinge on this. But it turns out that there's a lot of problems which are really substantive problems where people make silly mistakes about very weighty issues. One classic one that this has been replicated in is actually stock and flow dynamics for atmospheric carbon. Because there's flows of entering carbon and flows of exiting carbon for the atmosphere. What would flows of entering carbon be to the atmosphere? Volcanoes would be actually a surprisingly significant one historically. Anthropogenic carbon dioxide emissions, another one. There's things from agriculture, etc. So there's entering. How about exiting? Exiting of carbon, exiting the atmosphere. Oceans absorb quite a bit. Plants on terrestrial plants and forests, so on, absorb quite a lot. And when you consider those, and you consider gaps between entering and exiting, you have pretty significant implications. It turns out that it's not a bad model for how atmospheric carbon works. You have flows entering and exiting, and you have a stock of carbon. And if you were to think about changing the rates at which carbon enters or carbon leaves, you have a situation where it can have significant implications for how that stock behaves. And if people are really off base in terms of how they think about dynamics of stocks and flows, how the flows relate to the stocks, they can come to very, very misbegotten assumptions about how things will behave. How quickly, for example, if you were to lower emissions, how quickly the stock of carbon would change, etc. So let's talk about each of these answers. So during which minute did most people enter the store? Anyone? Okay, so it's sort of a matter of probably seeing it. It's 4 here, I think. Yeah. Which minute did most people leave the store? Yeah. That's right. During which minute were most people? Oh, maybe I'll ask a question that's not in here. During which minute was there the greatest net sort of change in the store's number of people in the store? Okay, 17. Yeah. The gap between this is largest. In this case, there were many more people leaving than there were entering, and so there was a big net change, right? During which minute were the most people in the store? Why is that? Okay, yeah. So up to this point, there were consistently more people entering than leaving, right? And so for each successive minute, there's more and more people in the store. There's more people coming in than there are leaving. And so up to this, it's been increasing. Now, in certain minutes, it increased faster than others. Like in this minute, it increased quite quickly. And this minute, it didn't increase nearly as much, and it's increasing less and less quickly. In what minute were there the fewest people in the store? Third. And why is that? Yeah, okay, so if we were to talk about this gap and total that, take the integral of this gap here, it exceeds the integral of that gap. So in short, there was some number of people in the store at the beginning, and it only went up from there, but then it went down subsequently at a level, it declined below the original. Now, someone could be excused for saying this can't be determined if you felt you didn't have time to sort of total up this area and compare it with that. So that's not totally, off base, but it turns this is considerably more than this area. And so the fewest people are actually in the store at the end. We have the store population rise and decline. So this is a common little problem. The statistics are such that it suggests the stocks and flows, people get easily confused. Fewer than half got it right for either of those two latter problems. And again, there were significant fractions that seem to rely on the flows, the size of the flows, as an indication of the size of the stock. And the flow was the max, they assumed the stock was the max. So we're going to talk more about this. You recall our discussion that stocks are fundamentally accumulations, and at a mathematical level, we describe them as state variables or compartments. Diagram them using notation, which indicates them as rectangles, and they lead to inertia in the system. That number of people in the store was large at that middle moment, and it only changes slowly as more and more people, net people leave. Talked about flows, flows being measured in some rate, some units per unit time. And we diagram them as these sort of pipes with valves on them. And one of the notions which I may have alluded to in a previous session of this class, but which is really an important one, and it holds throughout this class, whether we're dealing with system dynamics, whether we're dealing with agent-based modeling, or discrete event modeling. System structure, the structure here of stocks and flows and their linkages, the presence of causal loops, reinforcing feedbacks, balancing feedbacks. It shapes behavior in fundamental ways. It may only allow for certain types of behavior, only admit certain types of behavior, where other types of behavior are just not possible because of the structure. So system structure is defined by stocks, flows, and connections, relationships between them. And the fundamental property we'll be seeing here is one of non-linearity. Behavior of the whole for many of these models is more than the sum of the parts. You couldn't anticipate how the model is going to behave from any one piece of it, and if you want to anticipate how it's going to behave with respect to some input, with respect to some external disturbance, you can't neatly take apart that input into some particular functional forms, like in sine waves. Figure out how it behaves with respect to each type of sine wave, and then figure out how it responds to the entire input. We can't do that with a nonlinear system. We can't easily decompose it into things which we know how to handle and then sum it back up. The type of things we do with impulse responses or Fourier transforms or Laplace transforms in EE, for example, and some other areas of engineering. Instead, what we have is a situation where the behavior of the whole is tangled. How it behaves with respect to each of those subcomponents is not independent, and we need to consider its behavior with respect to the input as a whole. in this case, stock and flow structure, including the feedbacks, determines the qualitative behavior modes that the system can take on. So I had started with, I think, this problem, or I stopped with this problem last time. So here we have constant flows, inflow and outflow. And I want to ask, what happens to the stock? After that little exercise we did, this shouldn't be so daunting. But what happens to the stock here? If I drew out the stock, what would it be doing over time? This is the inflows. Inflow red, outflow blue. Okay. Okay, good. And how does it increase? Does it increase faster and faster, slower and slower, linearly what? Linearly. And yeah, exactly. Because the difference between the top one and the bottom one is a constant. Therefore, the derivative of the stock, the net flow into the stock, is going to be a constant. So we have something like dxt equals alpha, right? And we could integrate that, multiply the dt on the other side, and integrate both sides, and we would get x as a function of t just being L times t plus some constant. So we get something like that. Now we don't know what that initial condition is. Without further specifying that, we don't have a precisely defined thing. That's why I said alpha t plus some constant, where this initial value defines the constant. But it goes up linearly and it declines. That's sort of the nature of the situation. Suppose we have these flows, where it goes up here and then declines. So here the inflow is the red and the outflow is, again, the blue. We're looking at two curves here. What's really the important thing? Can we think about this as only, can we reduce the problem to just one curve? How do we do that? Oh. My movie of 371 is all set. Okay. Sorry. That'll be uploaded to YouTube shortly. So what can we do to reduce this to a single curve that we have to worry about? We could subtract the two, right? So all we have to really consider about is the net flow. And actually, it turns out that's just the derivative. The net flow, consider all the stocks, consider a given stock, all the flows out and all the flows in. If we consider flows in minus flows out, net flow, that's the derivative. So we could consider the net flow here. The net flow initially is negative, right? Because we have an outflow greater than an inflow. The blue is greater than the red. And therefore the stock will be going water's going out more quickly from your bathtub than it's coming in. The bathtub will be going down. At what point is the bathtub, at what point or points is the bathtub in stasis, in equilibrium, not changing level? Where the two lines come, right there. When will it be going up? Sort of, over what regions will it be going down? We've talked about one of them. Where will it also be going down?
We're all scared.
There, okay, to the right it will be going down. The inflow is less than the outflow, so it'll be going down. When will it be going up? Yeah, there. And it will be in stasis there. So, okay, so it's going up during this time, but what's the significance if there's a larger and larger gap with inflow from outflow? It'll be going up faster and faster. When will it be going up the fastest? When will the sort of rise of the stock be at its fastest value? The rate of rise. Months 75, that's right. When that gap is the largest here, the gap with the inflow being greater than the outflow. And then during this period, will the stock still be going up? Just be going up slower and slower until it will no longer be going up. Well, when will it be declining the fastest? Yeah, like down here. That's good. Okay. So this is this is what we get. The computer's a lot better at doing this than we are. You could be Albert Einstein, and it's still going to be more convenient to do it on the computer. But this kind of validates our intuitions. We look for points of reference, when it's going the fastest up, when it's going the fastest down, when it's at what points it's in stasis, and it lines up. And this curve is what sort of curve? This green curve, if we had to describe it, it's drawn from what family of curves? It's a quadratic. Because its derivative is going to be linear. The derivative of that is going to be constant. So here we have a situation where we have a quadratic change. So we just saw that. Okay. Now within these models we're going to be dealing with, it's going to be, guess what, folks? Quite a bit more complicated than this, because these flows, which are going to drive the stocks, are going to depend on the stocks for how they move. So there's going to be these feedbacks. The flows depend on the stocks, and the stocks, their evolution is going to depend on the flows. So here we had some very well-defined curves associated with this that we could follow, and even more so here. But in reality, what we're going to see is that our flows are changing, and they're changing based on the current value of the stocks. So the flows at any one time are going to be dictated by the by the stocks. So stocks are always changed by flows, and in these experiments we've used constant values for flows. Well, okay, we had linear there. Okay, so in general the flows are depending on things that are changing the stocks. So we might have something like this, or we might have something like this. And we're going to, in fact, talk about this one. So in general, this is what's called a first-order delay, and we're going to examine this in greater detail. But suppose we have a situation where we have an inflow to a stock and then an outflow. And the formula associated with the outflow is the stock divided by the delay. In other words, this flow out, let's suppose the inflow is constant for simplicity. This flow out is going to be this first situation where we see a flow depending on the stock. In this case, the rate of that flow is just going to be the stock over some delay. Okay? And there's a reason we call it a delay. It's a time constant. It's actually going to reflect the average time someone, if they come into the stock, how long on average will take before they leave. Okay? That's what it's called, a delay here. We could just as easily refer to as stock times some coefficient, which is 1 over delay. It's the same mathematically, but for now we'll just phrase it as the stock divided by delay. So this flow, to be clear, is changing over time. The rate of flow out is changing over time. It's like Lake Diefenbaker, as its amount of water in the lake goes down, if they're leaving the dam settings, similarly it's going to have slower and slower rate of water leaving it. The number of cubic meters per second leaving Lake Diefenbaker will be lower if the lake level is lower than if it's higher. So it will vary with the lake level. And this flow is going to vary with the stock. Okay. I'd like to talk about the equilibrium. I'd like to talk at what situation this stock will be in balance. Okay. This will come back to our discussion of balancing loops and so on. At what point will this stock be in balance? Under what situation, at a high level, I'm just looking for a very high level description right now, will this stock not be changing? Okay. So in short, what equals what? The inflow is equal to the outflow. Right? Under what situation will the stock be rising? Inflow is greater than the outflow. So the number of people entering the store is greater than the number of people entering the store per minute is greater than the number of people leaving the store per minute. The rate of entering the store is greater than the rate of leaving. Yeah, the inflow is greater than the outflow. And under what conditions will it be declining? Thank you. Thank you. Put me out of my misery sometime. Good. Okay. So suppose we have a rate of I coming into a stock where I is fixed. Okay. Under what would the value of the stock have to be such that the stock is in equilibrium? Yeah, inflow times the delay. And why is that? Because if the stock is value of inflow times the delay, then what equals what? So stock here is inflow times delay divided by delay gives inflow, so the outflow is equal to zero, right? Okay, so in other words, if the stock has a value, if it reaches a value of inflow times delay, then we'll get a situation where the inflow equals to the outflow. Now suppose that the value of the stock is below that. Suppose the value of the stock, suppose it starts empty. What's it going to do? This stock started empty. Is it going to go up or down? Why? There's nothing flowing out and the stuff is flowing in, so it's going to be going up, right? And it'll keep on going up, in fact, as long as the inflow is greater than the outflow. That is, as long as this stock is less than this value, the inflow times the delay, the stock will keep on going up. At that value, it will stop. How if the stock starts at a value above inflow times delay? What will it do then? It'll be decreasing. Why is that? Because the outflow is greater than inflow. If we have a value for the stock which is greater than inflow times delay, dividing it by delay, we yield a value that's greater than inflow, and so it'll be decreasing. And it will decrease to that equilibrium point, okay? This is going to be, and this stock, not surprisingly, exhibits a, what sort of feedback? Can anyone read it here? What sort of feedback is it? If the stock goes up, does this go up or go down compared to what the value it otherwise would have had? What sort of link is it? Plus or minus? It's a plus. Stock goes up, stock divided by delay, it's going to go up, all of the things being equal. I'm assuming here delay is positive. It normally would be. Okay, so this is a plus. Where's the negative? What sort of loop is this? It's a negative feedback. Yeah. It's going to lend itself to stability, pulling it back. This stock is being pulled back to this value of inflow times delay. You lower the stock, it's going to go up to that value. If the stock is too high, it will come down to that value. It resists perturbation. This is a negative feedback. Positive, the negative is staring me right in the eye. The negative link here. You increase this, it tends to lower that compared to the value it otherwise would have had. In other words, if this goes up, this tends to go down, all of the things being equal compared to the value it would have had. Okay, let's just go through that in mathematical terms. I want to emphasize we could have written that as some alpha times x instead of, I want to emphasize, this is stock over delay. We could have written it as some alpha times the stock, and alpha would have then just done the reciprocal delay, 1 over delay. Could have just as easily written it like that, in which case we have this relationship for the equilibrium value of the stock. Okay. Turns out we can represent first order delays as representing an approximation to a population undergoing transitions, stochastic transitions. Okay, it's deterministic. It's a deterministic approximation. But we could imagine, for example, this stock holding people, and a person has a certain chance per year of mortality. And this is the average lifespan of a person. And they will tend to leave here on average after that lifespan. Okay? Some will leave earlier, some will leave later, and we could think of this as kind of approximating that departure process. We term it memoryless because the chance of a person leaving in the next unit of time is independent of how long they've been there. They're all interchangeable in that stock. It's kind of like water in your bathtub. It doesn't matter how long that molecule's there, its chance of going out. That's the approximation. It turns out that we'll see probably in a little bit more detail later in the class. What this means is there's a distribution associated with how long do you spend in that stock. In the distribution, I think people here should have taken at least probability theory, and the distribution is an exponential distribution. Okay, so the amount of time you actually spend in the stock is exponentially distributed. So you have a higher amount of chance of spending less time, but you have some chance you could actually spend a long time in that stock. There's a distribution of how long people live. Some people, some infants die early on. Some people live quite long. So there's some distribution. In this case, it's exponentially distributed. I say it's memoryless because there's some chance per unit time of someone dying here, and it's independent how long they've been there, as we said. Okay, so I want to talk about this stock. So a stock like this, a first order delay like this sort of situation where we have formula here being formula for the number of things in the stock divided by some mean time, or equally stock divided times 1 over the mean time, some rate, in other words, some coefficient. Turns out that it leads to dynamics like this. This is actually, as we'll see, exponential in terms of the number of people remaining in that stock. This is with no one coming in. For simplification, we're just going to leave that out for now. We're going to imagine some number of people starting here. How many people are in this stock over time? The reason I'm emphasizing this is twofold. Number one, this is kind of the easiest situation to get exposed to this idea that flows depend on stocks and stocks depend on flows. Okay, so this is kind of duality here, and I want to make sure we get a comfortable with this idea, because the models we're going to be looking at very much will see stocks depend on flows, flows depend on stocks. Okay, so that's one thing. Second thing is bigger models are often built out of building blocks of these first order delays. So if you can understand it, you'll go a long way towards understanding bigger models. It's kind of like understanding the statements in Java, or the select statement in SQL. You'll get and understand how to compose things. Okay, so let's talk about these. Here's a dynamics of a stock. And it turns out that the stock will be declining exponentially like this, the value of the stock. And the value of the flow out will be declining exponentially, because the flow out, after all, is just the stock divided by some constant. Okay. Now, there's some continuous mathematics behind this that I want to discuss, we should be comfortable with. So if we represent the number of people in the stock, the size of the stock is x, we can again talk about x divided by some delay, or we can talk about x times some alpha, where alpha is 1 over the delay. Okay? Talk about easy one. Here we'll talk about alpha. So we'll talk about the outflow being x, the rate of outflow, people per year being x times some alpha. Okay? Where alpha is some chance per unit time that someone will leave. Per unit time likelihood of death. I want to emphasize this. If I were to say, what sort of properties does a probability have to, so you've taken a course in probability, what sort of properties does a probability have to be considered a legitimate probability? What values can it take on? It has to be non-negative, between 0 and 1. So that's good. It turns out that we're talking here, though, not about a likely, we're talking about a likelihood density. Now, you folks from physics or engineering physics will have seen this more and probably be more comfortable, but I want to make sure people are comfortable about this. We're dealing here, again, I'm going to state this again, we're not dealing with a probability. Alpha is not a probability. Alpha is a probability density. It's a chance per unit time, a likelihood per unit time. So it can actually be bigger than 1. It has to be greater than or equal to 0, but it can be larger than 1. If it's larger than, let's suppose it's 2, that just means, in this case, that on average, you'll tend to leave the stock in a time of 1/2. If its value is 10, on average, you'll leave in 1/10 of a time unit. So it's per unit time likelihood of death in this case, or likelihood per unit time. Because it's per unit time, it's, you know, that denominator could be very small, it could be larger than 1. Okay. When we have a likelihood like this likelihood density of this sort, we could talk about the chance of death over some small dt as being alpha times dt. Okay. So if alpha is 2, and we consider a small time unit, let's say 100th, there's going to be a small chance. There's going to be a small chance of death. Say time unit of 1/100th of a time unit. Maybe the time unit is a day, so this is 1/100th of a day. And maybe alpha is 2, and so that's the chance of death over that small period of time is roughly 2 over 100. Okay. If we have X people at risk, X being the number of things in the stock, could be people, it could be cars, what have you. The number in this case, we'll phrase it, dying over time dt is X times the likelihood of death over this delta t. X times alpha times dt, or X alpha times dt. Okay. So in other words, each person, each of these X people has a certain chance of dying as given by alpha dt. So we have X times alpha times dt as sort of the number that flow out on average within that time dt. Okay. When these people die, they flow out of the stock. So there's a net change in the stock that's negative. So we have dx, number of people in the stock, equal to the change in number of people in the stock equal to minus because they're leaving this number of people who have left within time dt. X, the number of people at risk, times alpha times dt, which is the likelihood that a person will die. So this is the fundamental equation that's governing this. Dx equals minus x times alpha times dt. And as x is depleted, not surprisingly, dx will be smaller and smaller. You have a quite linear relationship here. So the smaller x's, smaller dx is going to be. Fewer people at risk, fewer people are going to be leaving. 0 people at risk, 0 people are going to be leaving. Does that make sense, people? Okay. So let's talk about this. So here we have, you know, the total change in x over time dt as given by this formula here. So this might be 20 people, for example, over a time frame of 0.1 year, and approximately 36.5 days. You know, we might have alpha being 1,000 people, alpha being 0.2, x being 1,000 people, and then dt being 0.1 year, something along those lines. Okay, so the rate of change of x over time dt, the rate of change of that, how quickly it's changing per unit time, dx dt, is just this minus this dx divided by dt, and in this case it's just minus alpha x. So in this number of people at risk times the death rate. Okay, that's the rate. That's the rate associated with the flow. How many people per unit time are leaving, right? Okay. And we often write this, and I'm going to use this notation in this class, is x dot, in other words, dx dt equals minus alpha x. Okay. So we go back to this. Here, alpha would be 1 over mean time until death. So instead of dividing by this, we multiplying times alpha, be x times that, and we can read off here, it's alpha times x dx dt. Okay, that's the rate of flow out. Okay. Now, we could approximate this at smaller periods of time, but I want to make sure that this continuous, sort of the continuous mathematics here is fairly clear to people. So if we're considering a very, very small dt, and we consider dt as going to 0, right? Very, very, very small dt. We have this obtaining this relationship. We have and we could simply divide by the 2 here, and we'll get dx dt equals minus alpha x. So the derivative of the stock is just the value of that flow out. So there's only one flow, right? Does that make sense to people? Anyone want to ask a question about that before I talk about how that gets integrated up in numerical integration? People? Questions? Going once. Going twice. Sold. Okay. Someday you may get to see me talking like one of the auctioneers here in Willis. Yeah, it's a lot of fun for sure. In case you've never heard. Okay, so let's talk about the flow rate dynamic. So if we're dealing here with small discrete periods of time, we're going to be actually integrating this up over small periods of time. So we might consider a small period of time delta t, and think about a small change over that time, delta x. And by the same token here, we get delta x over some small delta t we'll assume is equal to minus x times alpha. This is the rate of the flow. This is what we're telling the model in our formula. X times some alpha. That's the rate of the flow. The flow is just alpha times the stock. Okay, that's what we tell it. And here we're going to have delta x, the number of the change in the stock over a given time delta t is going to be given by this. Okay. The rate of change of x over a given time is delta x delta t, and again it's this value here. In this case, what we're going to be doing is stepping forward. For Euler integration, we're going to be stepping forward time step by time step. What I want to emphasize is that the flow rate will be changing over time. As x changes, the flow, alpha times x, is going to change. And so it's going to change this right-hand side over time. But let's talk about this. So suppose x, the initial value of the stock is 1,000. Delta t is 1. Okay? We're going to be just doing this in a very coarse way at first. And alpha is 0.2. Okay, we're going to start with a stock of 1,000. Within this first time unit, we're going to have the rate of the flow, which is something we've told it. We've told it the rate of this flow. It's x times alpha, and it's going out, so it's minus alpha x. And it's delta x over some delta t, so we're going to have the change in the stock being the rate of this flow times this delta t. And here we're going to have 1,000 times alpha, 0.2, 200 times delta t being 1. We're going to get 200 tons, right? So delta x within this first time unit is going to be minus 200. So it's going down from 1,000 to 800. In this next period of time, we start with 800. Take that, multiply using the same formula, get 160. Subtract that off 640, so on. So in each case, we're computing the delta x. In short, we're computing the value of the flow. I'm describing here how the system dynamics package is working behind the scenes. It determines the value of the flow based on the current value of the stock. This is the important thing. And then the value of the stock is updated such that the change that's implied by the flow is realized. So the stock is updated, reflecting the flow out that occurred. This flow is computed, the stock is updated, 640. Now what goes on, going down from 800 to 640 because it's subtracting off the 160. This goes on across an entire model at once. It'll be computing all the flows in just this sort of way, using the same sort of approximation, figuring out the value of the flow as given by you folks, as told in the software. You're going to give it the value of the flow, and it's going to go through and compute using this formula, the value of the flow. Obviously, whether it's minus or plus is going to depend on whether it's inflow or outflow, times some delta t. It's going to figure out what the value is, figure out the value of all flows across the entire model, and then in lockstep, update all the stocks. Next time step, figure out all the flows based on the current value of the stocks, and then lockstep, update all the stocks, go into the next time step. Figure out all the flows based on those current value of the stocks, update. So we have flows, their value is going to depend on the stocks. It's the simplest case you could find where the value depends on the stock. So the value of the flow depends on the stock in this time step. And the value of the stock in the next time step depends on the value of the flow in that previous time step. You see that? So you have this updating. And what I want to communicate here is that the updating is occurring across all stocks at once after all the flows have been determined. So there's no issue if does this stock get updated before that stock. That's irrelevant. All the flows are determined based on all the stock values at time 0, for example, and only then does any of them get updated. And they all get updated at once. Does that make sense to people? So all these stocks get updated in lockstep, time step after time step, based on the values of the flows in the immediately previous time step. Okay, now I want to emphasize here that we have a flow rate. In this case, the flow rate is just the same as delta x, because delta t is 1. So delta x divided by delta t is just going to be the same value as delta x across the board. Now we're going to go to a finer time step. We used a kind of crude approximation here. We used delta t equals 1. In calculating the change, delta x, from x to, so if we're at time t and we're considering the change, delta x, from time t to time t plus delta, here t plus 1, delta t is equal to 1. We're assuming that the flow rate during that time stays constant for all that time step, right? So we're assuming here that when we're taking this change in x over this entire delta t, we're just taking x times alpha as the value of x it has at time 0 exactly, and then we're going to be multiplying times delta t. In fact, what's going to be going on during this delta t, going on during this first time step, is that x will actually be dropping. I mean, it'll be dropping in there, but our approximation to it, in continuous terms it'll be dropping, but our approximation assumes that x is going to hold this value, the same value it had 1,000, all throughout this delta t, and we're using that to determine delta x. So it's a pretty crude approximation in this case. Here we're assuming a pretty long time constant compared to how quickly it's changing. Given that the value of the stock here declines by about 20% within that first time unit, from 1,000 to 800, it's not a very good assumption to assume it has a value of 1,000 all through that time. In other words, that x remains at 1,000 for this entire delta t, which is what we're assuming by making this 200, right? By multiplying this out. So we can do it much finer, of course. We can do it half a year at a time step, for example. Here, we're doing it at a much finer time step, half that time step. So here, we have 1,000. The change in stock is going to be that same formula for the flow. This is mechanical. This is just plugging in whatever flow you've told it in your model. Okay, whether it's in or out, it's just going to determine that, again, mechanical times delta t. Here, delta t is half. So this is going to be minus 100. Delta t is a half, so it multiplies through. And then, but the rate of net flow, delta x divided by delta t, is still going to be 200. The rate of flow, people per unit time, delta x divided by t is still that 200 here. So, excuse me. So this is bogus. This is bogus. Okay, I'm gonna have to correct that. Please ignore the. Okay, so here we have a rate of flow out of 200. That was the rate of flow. We told it x times alpha. It's still 200. Alpha is 0.2. X is 1,000. The rate is still 200, but it's only applying over delta t that's half of that. So here it's going down from 1,000 to 900 in that first time unit, and then it's going down from 900 to 810, right? Okay, now if we were to look at this and line them up, here's a value of 0.5, here's a value of 0.25, and what you'll notice is there are significant differences. This initial one was indeed a crude approximation, and it becomes evident even in the first time step. A difference of 10 here, a difference of 14 against 0.25. You know, if we look later, we'll see even more significant differences. By time step 5, the gap between these is, you know, very large indeed. It's over 30, for example. Nearly 10% of the value, and at this time frame here. So there's big disparities. Now, both Vensim and any logic have a step size, which is going to dictate this. The step size in general, this delta t, is going to be dependent on the time constants in your model. What I mean by that is if things are executing, if things occur very, very quickly, if alpha, for example, is very large, then the time constant will have to be smaller to allow it to actually accurately compute it. If alpha is very, very small, things only, instead of 0.2, if it were, you know, 1 out of 100, it turns out that the time constant could be quite larger. It's actually the ratio between the time step as compared to the shortest time constant associated with the model. So here, alpha was reasonably large. It was 0.2, and a finer time step is advised. If we look at this, you'll see that as you run it with different time steps, it gets closer and closer approximation to the continuous value. The continuous value associated with this is in fact it's going down exponentially. It's going down as this, and we'll see this. It's declining exponential in that form, and you should become very familiar with that. We'll discuss that further. But the point is, in this case, we know the closed form expression. For most models, we don't. But one thing we could do is lower the time steps until it converges, until it yields consistent values. Okay. Now, this is kind of a simplistic approach to it, but it's one that's often taken. Lower the time constant until things converge, till they're consistent. Lowering it one more time unit doesn't really seem to impact it much. An alternative approach that's more sophisticated will be what? Those who have taken differential equations before should be able to probably mention to me a more sophisticated way to deal with a situation like this. Anyone make a suggestion? What sort of integration have we been looking at here? It's called Euler integration. And it turns out that that's kind of the simplest scheme. It's very good, it's very widely used by many people for whom their models are simple enough, or They don't have to simulate it at too fine they don't care about simulating it too fine a time step because it's still very quick to integrate out. It's perfectly fine. But it turns out that if you have a really quite sophisticated model, a model where what is called stiff, then you're going to have to integrate it at a level of temporal resolution, a level of time resolution that's much finer than you care about, okay, than you require. And for a small model, that's not a big deal. We might do that here. We might not really care about looking at things at, you know, 1/500th of a time step or what have you, but we're perfectly fine simulating it. VenSim is extremely fast doing that. But as the model size grows, that may not be so feasible. As you get a model with thousands of stocks, etc. And in that case, you can use what's called, for example, Runge-Kutta methods, Runge-Kutta integration. And there's a whole family of Runge-Kutta methods which vary in their sophistication and their order of convergence, as we say. And what that means is essentially they can simulate things in a more economical way, and they typically do so by, for example, choosing variable time steps, so it's not just a fixed time step. Perhaps choosing a time step based on how quickly the system is varying then. If it's not varying quickly, you make a big time step. If it's varying very quickly, then you make small time steps. And VenSim and AnyLogic both have support for Runge-Kutta methods using this sort of approach. I'm showing you here the most simplistic version, and the main thing I want you to carry away from this is, number one, the time step can be important, and you want to look at that, because if your time step is too crude, you can get numerical artifacts. What I mean by that is that the behavior of the model could diverge from the actual mathematics, what the actual mathematics would imply, and you may be fooling yourself. You'll see behavior coming out of it that is in fact not representative of the underlying mathematical system. If you are careful, you'll examine for ranges of time step that are quite small, and you'll find, okay, it converges at this level of behavior. I don't need to go smaller than that. But the other thing I wanted you to understand is this whole lockstep evolution of, on the one hand, the stocks, and on the other hand, the flows. It's extremely important to understand the values of the flows at a given point in time are computed from the stocks at that point in time. Based on those flow values, time says dt, it'll update the stock values for the next time point. Okay? So I want you to come away with that. So in this case, we can arrive at what's called an analytic solution of the model. What I mean by that is we can actually write down an exact formula for how this model is going to behave. For most models, we can't do that. In this case, I've deliberately chosen a simple enough example that we can. We can write it down using simple functions that are going to be familiar to us. So in this case, we have something like this. We should be able to, you should develop the skill of being able to look at a stock and flow diagram and write down the differential equation from it. In this case, what will be on the left-hand side, the state variables whose derivative is on the left-hand side, are going to be simply the what in the model. What are the elements of the model called the state variables? They're called the stocks in the model. The right-hand sides are all going to be elements of the flows. Okay? Flows out with a minus sign, flows in with a plus sign. So for a given stock, what you'll have on the left-hand side is the name of that stock, you know, D stock dt basically. The stock is named Y, dy, dt. On the right-hand side, you'll have terms for each of the flows. You have plus for in, minus for out. And this is just the formula. Right here, it's just the formula you will dictate. Whatever the formula is for that flow in VenSim or AnyLogic, that will be the formula right there. Okay. In this case, it's trivial. I shouldn't say trivial. In this case, it happens, it admits to a solution in closed form. So here we have dx dt equals minus alpha x. And turns out that if we have this in a trick you probably learned very early on, if you took differential equations, we can simply separate the variables, divide x over here, dt over there, and we can integrate both sides. What does this integrate to? Can anyone tell me? We can integrate both sides from 0 to t, where 0 without loss of generality is the first time, the initial time of the model. If we integrate this, what do we get? Yeah, natural logarithm of x plus a, well, yeah, actually a constant, but then that ends up canceling because of this thing here. Okay, and then on the right side we get what? We're integrating this dt, so we get alpha times t, and it's going to be a value of 0. And there's a constant, but again, it's going to cancel. So here we go. And you do this, okay, so we get ln of t minus ln of x at 0. And basically you do the math here, and so this is the result of the integration right there, as we were saying. And this just expands into this. We evaluate this at t minus this value at 0. And over here it's just alpha t, and it's minus alpha and 0, so we don't even represent that. And then we can move things around to put this on the right-hand side, just rearrange this and write this more nicely in this sort of form. We put this up in this because we take the exponent on both sides. So this ln goes away because we take the exponent on the left side, we take the exponent on the right side, we get this, and we get a sort of multiplication. Okay, so what is this doing? Can anyone describe to me what this is? So this is the initial value, and this is times something, which is a what? Declining exponential. This is what it looks like. If you have, assuming alpha is greater than 0, which as a rate per unit time, I'm going to assume. So here's t, and we have this. So it's a declining exponential. What's the value of this guy at t equals 0? Does anybody check? 1. Yeah. So in this case, this whole thing is going to have a value of x of 0. Okay, it has the initial value of the stock at time 0, and then it's going to be declining exponential. Now, this makes some sense. I mean, if we look back at this, the rate of change of the stock, how quickly it's declining because it's a minus, is going to depend directly on how many individuals are in here. So at first, it's going to be declining faster. The number of people per unit time who are leaving, the rate of change, the rate of decline of this is going to be larger at first because there's more people to leave, right? X is going to be larger. As x becomes smaller, the rate at which it's declining is going to go down. And so it's going to decline faster at first. The slope is going to be steeper at first. And then the slope is going to be slower later. It's going to get slower and slower. So we're going to have a less and less steep slope over time. And it's going to follow in that exponential fashion. Okay, so that's good. If we consider no outflows, we could ask what fraction the people who remain there after a given amount of time, and that's just x at t, which we have given this formula, divided by x of 0, which is just this. So the fraction of people that remain is given by this. Or your likelihood of remaining after time t is given by that. Given that you have a certain chance per unit time of leaving, if you haven't left already, of alpha. So if you have a 1% per day chance of, oh gosh, I gotta think of something not so horrible. 1% chance per day of winning the lottery or something. Your chance of not having won the lottery after a certain amount t goes down as that. Now, in the case of the lottery, alpha is about 1 over 1 over a billion or something. So don't think it's going to decline too steeply. In your case, you could be waiting a long time. Okay, so given that people either stay in the stock or leave, the fraction that have left by time t is just 1 minus this. Okay. So for a given individual, the chance they remain goes down as this, and the chance that the fact that they have left goes down, changes as that. So over time, this is going to approach what? This is going to approach 1. Yeah. Okay, so if we consider at time 1, we have a certain fraction we've left the stock, e to the minus alpha we've left the stock, and you know, if you have a very small alpha, or you're considering a very small t, you can actually approximate this as alpha t. These higher order terms actually end up being kind of ignorable, and you know, for very, very small t or very, very small alpha, what you'll get is this thing equal to approximately 1 minus alpha t. So so by time 1, for very small alpha, approximately 1 minus alpha will remain, and a fraction alpha will depart. Okay. The initial, what's the initial slope of this guy? If I were to take the derivative of this around 0, what's the slope of it? If I were to evaluate this at 0, what's this at 0? People said earlier it's 1. What's the derivative of this at 0? Yeah, exactly. So here, if we take the derivative for an exponential, you may recall that we're going to get minus alpha times like that, and around t equals 0, this is going to be 1, right? And we're going to have minus alpha. So the slope of this here, it's going down this way, but it's the slope initially of alpha, right? And as time gets on, it goes lower and lower. So initially, you know, you're having a chance alpha of leaving during that time, or that fraction of the population alpha is leaving at that initial time. Okay, now let's talk about the mean time to transition. So if we wanted to, I made a statement earlier about how likely the average time it takes for someone to leave, but let's look at this. If we want to consider the average time for a given person in the stock to leave, well, we could deal with, okay, what's their probability of leaving at between time t and time t plus delta t, and multiply it times t. That will give the average time at which they leave. So integrate up here. If we integrate up x times the probability of x, we get the mean value of x, right? So if you integrate up t times the probability that we're leaving between t and t plus delta t, we get the average time t of leaving. Here we have a sort of finding out the mean. Time is short, but I presented the sort of full reasoning here about how one derives this. And you know, fundamentally, we need to reason about the fact that, okay, you know, your chance of leaving before time 0 is 0. For time greater than 0, we have to think about the fact, okay, well, what's the chance you're still in the stock? And then, given that you're still in the stock, what's your chance of leaving per unit time? Given that you're still in the stock, your chance of leaving per unit time is what? Given that you're still in the stock, the chance of leaving per unit time is, yes, it's alpha. Exactly. Exactly. That is the key thing. So your chance of leaving per unit time, if you're in the stock, is always alpha. Now, more people will be leaving earlier than later because there's more people at risk of leaving. But your chance of leaving per unit time is always alpha. This is a key thing to understand. Your chance of leaving is always alpha. Now, you're still more likely to be leaving earlier than later because there's a larger number of people at risk of leaving. So if we ask when do people leave, more are going to be leaving early than later. But this walks through the basic theory. So we have to basically ask, okay, we want to see the likelihood of a person leaving exactly between time t and dt plus t, and here we have this fact that probability that you've not left by this time is e to the minus alpha t. So what we want to compute here is probability of leaving between time t and t plus delta t, given that we have not yet left by time t. And we can compute this through. I'm going to leave this for your reference, but fundamentally, this is the formula for leaving the chance that we're leaving exactly between time t and t plus delta t. This is the formula for that. Here we have a certain chance remaining there, and given that we're remaining, this is our chance of actually leaving during that time, delta t. So alpha times delta t times this probability we're still there. So if we integrate this up, it turns out that we're going to need to integrate t times this guy, because again, the idea here is it's like we're summing up each successive value of x times the chance of having that value of x. And we're going to sum that up to get the expected value of x. Here we're summing this up. It's just like doing continuous summation to find out what's the average time of t at which we are leaving. And so P of t times dt is the chance we're going to leave between t and t plus dt, and we're going to be multiplying times t to get the average t at which we're leaving. Okay, so we can compute that expected value by integrating this up, and it turns out that for those calculus geeks like myself, how would you integrate this? It's by parts. Yes, someone else likes it too. Okay, good. Man. Okay, so we integrate this by parts. It's a thing of beauty. It's a joy forever. Trust me. I know, you're probably glad for me to have the joy. But it is a beautiful thing. Okay, so we solve by integral by parts. And this is what we get out. Okay? We get out this from this integral, and so it turns out we're gonna multiply it times, we have to multiply it times this alpha times the results of this integral of 1 over alpha squared, and it turns out this is what we get. So folks can take it on confidence, or you can look through it. It's actually beautiful math, but this is the average time until you leave. So if you have a chance per unit time, let's say you 1% chance per day of winning a raffle, charity raffle. If you have a 1% chance per day, the average time it will take you to win that is how many days? 100 days. 1 over that. Okay. So, less favorably, less optimistically, if a certain rate of diabetes, the mean time it takes to depend is just 1 over the reciprocal of that rate, 1 over that. Okay. Okay. So here, this alpha, your average time to leave via this is just 1 over that thing. And that's why, folks, to sort of give this a, perhaps it won't be a dramatic unity to you, but there's a unity to it. Let's go back to this case. Remember early on I said you could represent this as 1 over a mean time, or you could represent it as x times alpha, where alpha is 1 over the mean time. So if you consider it as x times alpha, then the alpha is just 1 over the mean time to leave. if you want to think of it, if you prefer instead to write it as some mean time, the formula is just the stock divided by that mean time. Okay? In either case, what you get is a situation where your chance per unit time is the reciprocal of the average time to leave this. So this is called a first order delay. The number of people leaving, the rate of people leaving, people per unit time, depends on the stock. The stock's value over time depends on the rate. So it's sort of the simplest building block. And it turns out that if you look at the sort of system dynamics models that are out there, built using this, you'll find that probably a good, you'll find first order delays appearing throughout those models. I'd say perhaps 60 to 80% of the relationships incorporate first order delays. Okay? So if you can understand this, you will be able to just start seeing these things scattered throughout your model. It's like seeing an assignment statement in Java or something. Once you know, okay, that's how you write assignment in Java, you will just, if you go look at these things, you'll just see it everywhere. Similarly with first order delays, if you keep these principles in mind, the flow, if there's no other inflows or outflows, the flow will go down exponential. We'll just drain it in this way. The mean time to leave is 1 over the rate, or the rate is 1 over the mean time. That is sort of the chance per unit time of leaving is 1 over the mean, and vice versa. That will get you a long way. Now, of course, these models aren't typically nearly so simple. What we're going to see is there's competing risks. So there's cases where there's several outflows, and we won't go into that, the detail. That's the most detailed calculus we'll see this semester. But what you will see is that when you have two flows out, there's going to be the average time to leave on any one of the flows is going to be affected by the other flow. If there's another flow out here, imagine there's another flow out from the stock, which you're really, really likely to leave in. The only way you're going to be going this flow here is if you go quickly, because otherwise you'll have been drained by that. So it's going to really skew how quickly you leave on average via this flow, the fact that there's another flow. If you're going this flow, it's going to be in the first few time units, or else you ain't going nowhere. Well, okay, you're going down there. So here, if we have two flows, they kind of compete with each other, and it's very, very elegantly described by this. And then we're also going to see that we can chain these together. So we'll chain together stocks like this, and any one stock is memoryless. This is the important thing to remember. Someone may have arrived in here from an inflow 10 time units ago or 1 time unit ago. As far as the system is concerned, it's irrelevant how long he's been there. The chance of leaving per unit time is the same. But if you start to string these together, one stock, one first order delay after another is no longer memoryless, in the sense that the system as a whole is no longer memoryless. If you enter the system later, you're more likely to be in a stock that's further along, for example. Okay, so stock by itself, memoryless. It doesn't care how long someone has been there, and people's chance for leaving here is just 1 over mean time to death. That's just what it is while they're in there. So we'll see these stocks a lot. One final thing I remember is that we are looking at the simplest building block here, and later we're going to be seeing situations where this chance of leaving is actually not itself a fixed constant. It's actually something that will be varying over time. It's something that will vary based on other stocks. So just remember, when the flows vary, they're based on the stocks in this time step. And in fact, if we have auxiliary variables, like a value here, that varies over time, it'll be doing so depending on the values of the stocks. Okay, so that's first order delay. Bit of heavy math. I would encourage you to take a look at it just so you can follow these things through. It's pretty well explained in the slides, if I may say so myself. Exactly. So, see if you could take a look at it. It's not going to be subject of heavy testing or anything, but it is helpful to understand why, and to be really clear about this issue. Your mean time to leave is 1 over the rate, and vice versa. Okay. Okay. So next time we will be going on to look at this issue of competing risks and this aging chains, and we'll see how bigger models are built up out of these smaller pieces, and we'll see why it's called a first order delay as opposed to an nth order delay. Okay. That's good. I guess that's all for today. I think you have your problem set you're working on. If anyone, I've had office hours which have been less heavily attended. But if you need to meet on the problem set, just let me know. Okay. Thanks. Yeah.
So, did you get my email?
Yes, I did. Yes, about this thing. Sorry, I had a big deadline yesterday, so I haven't gotten a chance to. So what I'd like you to do is, so I need to write something.
Yeah.
Now, does it need to be on letterhead, or can it be email?
I didn't. I'm not. I think it's just email. That's
Okay.
fine. Yeah.
So what I'd like you to do is, I need you to remind me.
Okay.
Okay.
Yeah.
So my goal will be to get this thing out by this weekend at the latest.
Okay.
Okay. If I can, I'd love to do it tonight, but I've got a couple other. There's a stock of things to do that accumulated during this other deadline,
Okay.
and so now I have to work through the stock, and this is one of them.
Okay.
I'll try to get to it tonight, but in any case, I want to get it by this weekend. So what I would like you to do is send me mail by Saturday evening, okay? If you haven't gotten confirmation,
Okay.
and we'll get her out.
Okay.
Okay. And so it has to go just to that person. Then the other guy has to send an email, and then that should be it.
Well, then it goes through a review by the vice dean of academic affairs or whatever.
Yeah. And do I need to sign something further?
No, I think we should be good once you send the email.